Okay, and it is my true pleasure to introduce Thomas Fiedler, who is the last speaker of this part of the of session one of the second part of the fourth day of the conference. And he's from University of Toulouse, and he will speak on this intriguing title, Distinguishing Nodes Without Invariants. So, Thomas, it is to you, and he will give a Blackboard talk. So how long have we not seen a Blackboard talk?
Okay. So, hi, everybody. So, I will give an old-fashioned talk, just chalk and blackboard. I hope it's okay for you. So I'm very happy to be here to celebrate Lou Kaufmann, whose work has such an immense impact on knot theory. And for me, his Kaufmann bracket polynomial is one of the most beautiful things in knot theory. And so it's no wonder that many people have generalized, extended, applied, refined this Kaufmann bracket. And there are lots of talks about this at this conference. And in some sense, my talk will be also one of them. So what is the Kaufmann bracket polynomial about? It's about resolution of planar double points. So my initial idea was, let us play the same game with planar triple points. Triple points, so the solution that would be three branches which at one point are projected to the same point in the plane. So of course, it's still work in progress, and it took me a long time to realize what is the main point. So what is the main point? The main point is one should use different types of Reidemeister moves in different ways. So I will explain to you what I mean by this in this talk. So triple points, of course, are not stable. If we move a little bit the diagrams, they disappear. But they become stable in one-parameter families. So the price to pay is that we, instead of zero-parameter families, just discrete knot diagrams, we have to consider one-parameter families. And then, of course, we have to consider also homotopies of one-parameter families. This is just two-parameter families. Okay, so let us consider two diagrams, D prime. And we consider the basic question, do they represent the same knot or not? First of all, we transform that into long knots. So we have here our D, it goes to infinity, to the left and to the right, and we call the point at infinity A. So it's on both sides here, this point at infinity. And it is well known that this is equivalent. Two knots are isotopic, two diagrams give the same knot, if and only if the long knots are isotopic too. So we consider the space of M the topological model space of all long knots. Because we are interested in diagrams, we fix once for all a projection into the plane. And we have then in M a subspace, an open subspace, which I call M reg, an open subspace in M, which consists of all those knots for which the projection is an immersion. Projection into the plane. Immersion. Okay, this is a space which we are interested in. So if our two diagrams represent the same knot, as well known, then there's a series of Reidemeister moves in which we can connect them. So there is a series Reidemeister moves, R1, R2, and R3. So what do we do with them? First of all, we get rid of R. We don't want any L1 moves. With the L2 moves, we construct support for an integration in MD. Okay, and with the L3 moves, we construct a discrete one form to integrate. Okay, so I will explain to you what does it mean. First of all, if I have my long knot, I can associate two numbers to it. There's the rise, V, and the width index. So just the algebraic number of crossing is just how, if I smooth it, how the number of circles which go in positive direction minus the circles in negative direction. And it is well known if here I have my D prime. If VD equal V prime, VD prime, and ND prime equal ND, and the knots are isotopic, then there's a regular isotope. But we can always achieve this by adding small curves, like that, and so on. That these numbers are the same. So we can always approximate loops, for example, by a regular isotopy. But we have to be careful. This is no longer true in two-parameter families. So there are loops in MREC, which are contractible in M, but they are not contractible in MREC. So we have to be careful with that. Okay. So what do we do with the Rademacher 2 moves? So assume that we have a regular isotopy now. We are now in MREC. We don't care no longer about Rademacher 1 moves, which goes from D gamma, say regular isotopy, to D prime. My D prime, my D. And I feel the crossing, the positive crossing, negative crossing, and so on. And I have crossings here. So on. And what I do, I just follow the crossings in our isotopy. So this here is my parameter, the isotopy. So here I have a positive crossing, and I follow this crossing in this isotopy. It could be that it dies together with a negative crossing in a Rademacher 2 that would look like that. And this negative crossing, they was born with a positive crossing in another Rademacher 2. And then at some moment it will go up to D prime. Or it could be that it will not go up to D prime. It will be like that. It come back as a negative crossing to D. Now, of course, here the same phenomenon will appear. So we have here positive to negative. So we see we have an oriented cobordism of crossings. So here we have for two moves, an oriented cobordism of crossings. We call it C, and we are interested in the connected component. You see here, for example, this is a connected component. They could intersect. In triple points, they would intersect. We don't care about these intersection points. We take this as a resolution, really. They are disjoint. So it's really the connected components of this cobordism. And we will integrate something over these connected components. Well, if we have a long knot, then we have immediately more information about the crossing. The crossings, each crossing has now a topological type. So let me draw a picture of that. Say here we have a long knot, which looks like that. I have just two positive crossings. We have two positive crossings. This here is my long knot. So goes here to infinity with A, and I put a meridian near to infinity. So nothing ever happens here. Everything is done in some compact region in S3. And if I smoothest crossing and go from the overcross to the undercross, I have here the small loop. I see this loop will not be linked with the meridian, and we will call this a zero. And if I make it here, you see the overcross from the undercross, what I get will be this line. So it will be linked with the meridian. So we call this a one crossing. It's very common to give this by a Gauss diagram. So we take a circle which parameters are not it's oriented, and for a crossing we make an arrow as a chord with a direction on the circle. This here will be always the undercross, and this the overcross. So this loop which we have considered is this loop which we get out of that. And here a zero crossing would mean our point A is here. If the point A is here, it would be a one crossing. Okay. So we have these two classes of crossing, and this is invariant on the components of the cobordism. On each component. Okay, so we have two sorts of cobordism: the cobordism of zero crossing, of one crossing, and we will treat them separately. Okay, what about the R3? Can one see it right on the blackboard? Is it okay? Okay. So in R3,
Yeah,
we have,
can see.
We have our projection in the plane, and at some point, we see a triple. That means we have three branches which cut this line for the projection, because we have the lowest, the middle, and the highest. So this gives us three crossings: this one, and this one. It's also very common to make it in a Gauss diagram. So we have the Gauss diagram like that. So this here will be the lowest branch, this will be the middle branch, and this here will be the highest branch. Okay. So this, we call this crossing the crossing ML, middle lowest branch. This is the crossing HM, highest middle branch, and this is the crossing HF, highest lowest branch. And somewhere here we have our point at infinity. For example, our A could be here. So we call this the global type of the triple crossing. Of course, it has also a local type, just the signs of the three crossings. Okay. So we have a global type of a triple crossing, but it was a Reidemeister move. So we come from one side and we go to the other. So we will have a sign of this move. So if the projection looks like that, everything is oriented, by the way, in my problem. If the projection looks like that, then the sign is always determined just by the planar picture. Then on one side, we have the three crossings corresponds to three chords like that. On the other side, are like that. So we say this is a positive projection. Okay. If it looks like that, then on one side we will see that. On the other side, that. And there we have no choice. This positive direction implies that this should be the positive direction. So triple crossing Reidemeister moves come with a global type and with a sign. Okay, what will we do with that? I think the best for understanding that is we will study a baby example. So let gamma be a generic arc or loop. So it's a regular isotopy, one parameter family, which is a regular isotopy. We associate to it is a covariance of the zero crossing. Consider only the zero crossings. And we we will define a one cochain, the integer one cochain. We will call it B2 CE. CE is a component of our cobordism of gamma. It's the following thing. We sum up our all randomized 3 move, which are of this global type. Here's the point infinity A. And this crossing ML is on the cobordism CE. So ML. And what we start is just the sign. Is this clear? So we consider the we have on this cobordism component, we follow this crossing. And each time a branch passes over this crossing in this way, the triangle should be like that, then we associate the sign of this move. So this is the most simple thing we could do. And the proposition is this is the one. So this is so easy that I'm ashamed to call it a proposition. There is some technology to construct one-code cycles, so discrete one-code cycles. So we have to solve the global tetrahedron equation, the cube equation, and the commutation relation. So it's rather complicated, but for this simple thing, everything is trivial. So this is really some triviality. So let's just apply that. Let's take a loop. So let's take the treatment. And we add 2 curves, one like that, one like that. So this is our first diagram D. Okay. And we take the connected sum just with not 5 1. 1, 2, 3, 4, 5. This is our D prime. Okay, this is the connected sum of a tree-file with the not 5 1. And we have add these 2 curves, so now they have the same right way and the same width index. So if they would be isotopic, then there would be a regular isotopy. Okay. So it's easy to see where the zero crossings. So we come from the overcross to the other. This is the zero crossing. This is the zero crossing. This is the zero crossing. Here we have this, this, and this. In each of them, we have 3 zero crossings. And it's easy to see that each zero crossing gives its own cobordism component. So what happens with the zero crossing? We still make this move. I haven't yet tell you what is the loop. So the loop we will call it slide. We make the first thing small, D. We have D prime, and we push it through D prime on the other side. And then we make D prime small, D big, and we push D prime now through D. It's like waving a braid from these 2 knots. So this is a loop. We come back to the same diagram. So in particular, you see immediately the crossings come back each to itself. And the cobordism will not be straight lines because we will have, of course, here randomized 2. They will just make some S curves in this cobordism. But there's a one-to-one correspondence of crossings with cobordism components. Zero crossing. And zero. So let's calculate our one-code cycle on that. It's a very easy calculation, but unless I have no time for that, I will just give you the results in red of this crossings. On this it will be -2, and this -2, -2, and here it will be -1, -1, -1. That's all. So what have we shown with that? We have shown 3 things. First, we know that this loop slide is of infinite order in MREC. So this is not new. Grammar knew already that's of infinite order, even in M. So secondly, if you take the sum of these numbers, this is not invariant. Sum over our I in the B line D. The costings in D is not invariant. We could do better, but just taking the sum is not invariant. If we make here a randomizer 3 move for our diagram D, it wouldn't change anything because it's 1 cycle. And if you make a randomizer 2 move, 2 new crossings would appear, okay, which belong to the same component. There are 2 new components. This, if we see now at the beginning of this diagram, we would put here component C1, here component new component C2, and whatever branch goes over, under, or between these two, you see we have 2 randomized moves. They have the same global type, and ML, which gives our composition component, is on the same component for both, and the signs are different. So it would just add 2 new numbers with opposite sign, so it cancels out. Okay. So we see here we have 6, here we have -3. So we have proven that the 3-1 and the 5-1 are different ones. 3-1, 5-1. That's not really new. I think we knew that already. But what is new? What is new? We have just to look at the randomized moves. What is the sign? And how many such moves? If the diagram D has C crossings and the diagram D prime has D prime crossings, then it would just be 4 times that move. So assume that we fix the knot D. We fix D. And we compare it with all other knots, D prime. So we calculate our invariant. So the complexity of the calculation would be linear in the crossings of the other knots. Okay, so we can distinguish our knot D from the other knots. Sometimes when the invariant is not equal, we have an invariant which is of linear complexity. Even if you take the simplest Vasiliev invariant, V2, it would be of quadratic complexity. So this invariant is more efficient than everything what we have ever seen. Okay. But we have also shown a third thing. Because these numbers are invariants of the cobordism component, we know no zero crossing of this knot. There couldn't be any regular isotopy which brings the zero knotting of this knot to any zero crossing of this knot. No regular isotopy. Zero crossing in D, zero crossing in D prime. Okay. This is not new either because of Schubert. We know from Schubert if we have a regular isotopy of this whole knot, because there's a unique prime decomposition of knots, so it has to bring this knot to this knot and this knot to this knot. So the crossings cannot mix. But Schubert is a difficult theorem because of the generality. But here, in this particular case, we have proven it very simple, extremely simple. Okay. So you see, so in this simple example, this little thing shows it's already interesting. So the hope is now that we can generalize that, what I've told you there, and we can perhaps go even beyond invariance. So I will tell you that now. So what is our object? We have a long knot D, a long knot D prime. And of course, they have same Whitney index, same price. We take an auxiliary knot K, a diagram which we know well. We know. And we assume that there's a regular isotopy from D to T prime. Okay, what we do then, we add the longitudes to all these knots, and we take the connected sum. of D with K and D prime with K. D, K. This was the point A. Here we have a new point at infinity B. So we call this here the point A now. This is the point A. So we identify this point with this. So if we close it abstractly, it becomes a circle. And we make, and now we make the same thing here. Here we have D prime. A. A, B. And we take half of our move slide. I call it push. We just push D, we make it small and push it to K. That's all. So we come here to K now. Yes. I call it, because we double this, I call it 2. I have to call it like that, 2K to D. And that means we have doubled this with the longitude. Because everything is framed, even more than framed, with written index, we can do that. A, B, B, A. And what we do now, we take our regular isotopy gamma, which induces, of course, an isotopy of the 2 cable of D. So here we have 2 gamma. Let's bring this to do D prime. Here we have 2K. And then here we take the inverse of the push of 2D prime. Here we take minus, so I call that the push D to K. I take minus push 2D prime to K. Okay, and here, of course, here for that is identity. Here for that is identity. And here, of course, I take minus 2 gamma. Gamma in the other direction. And I get a loop. When we close, we come back to that. This is a loop which we call push to gamma. And M leg at a loop is a loop. So this is instead of a couple of diagrams D prime, we will study this loop. And we know D is isotopic to D prime. Expression we are interested in, if and only if the loop push to gamma exists. So we need these regular isotopy exists. So this loop exists if and only if the diagrams represent the same knot. And so we will use that. So what is the basic property of this loop? So I will not erase it because we will use it. Basic property. It's contractible in MI. So the contraction is a 2-parameter family. In general, we cannot avoid cusps, but here in this case we can. One see immediately the contraction. What we do is just we make the 2 gamma just shorter. We end up earlier before we come to this, and we can still make our push in both directions. There is no obstruction because this thing is small. It's still whatever we do, we can make our isotopy at the same time as pushing it. And we make it so this contraction in a very nice way. We just make the 2 gammas shorter, and so this square will come to this arc, which we go twice, and then we contract this arc just in the starting point there. Okay, so this is a contractible loop. So what we now want is just 1 good cycles. So I assume we have a 1 good cycle Y. No matter it represents the trivial cohomology class or not, we evaluate it on this loop. It has to be 0 because the loop is contracted. So 1 good cycle. Right. Then we know that I on push to gamma is 1. Okay. So, yeah. Which is the type of one-code cycles we want? So, definition. I one-code cycle in Emmerich. We call it peripheral. Right. If it satisfies two conditions. The first is if we forget the base points, we have now a couple of base points, A, B. If we forget the base points, we cannot extend it to a one-code cycle in the solid torus. So if we forget the base points, we could close this here behind, and we take just a half twist into K, and it would be a knot in the solid torus. So we could consider this one-code cycles and not in the solid torus. And this definition should not allow this. Okay, that means base point is important. If base points important. Cannot forget. If we forget one of the base points, we consider our formula. We have still a one-code chain. It should no longer be a one-code cycle. So that means that we have added here a longitude is important. If you forget that this is longitude, if you forget one of these two base points, it will just be a long knot. Okay, which is a little bit strange, but it's the same. We have exactly everything the same here, but it should no longer be a one-code cycle. So base point important, so longitude is important. And the third, I is a one-code cycle already on each component of the covariism of zero crossing. E one-code cycle on each zero crossing. Yeah. And it's not the one-code cycle on the one crossings. So that means we use the meridian, because we have seen in this distinction, we use the meridian. So in other words, what we use is the peripheral system. We use the longitude, the base point, we have even two of them, and the meridian. Those Waldhausen tell us this should we do. So we listen to Waldhausen, okay? And we will not use the knot group, because Novikov-Faser tells us that it's not a good idea to use the knot group explicitly. So how to get these one-code cycles? I'm a little bit running out of time. So I have to tell you a little bit about the zero-code cycles. Combinatorial zero-code cycles. So there's a very nice work by Chmutov-Polyak, which tells us how to construct them. I think it was 2009 or something like that. So he takes the Homfly polynomial, Homfly PT polynomial, and P plus minus R minus 1, P minus, that is 0. And it makes substitution a to the exponential to the power of r, and then takes the power series expansion. So P becomes the sum KL n PKL, HK, that. So in each coefficient here, these are the coefficients. Each coefficient here is a finite type invariant. Of degree small equal to. Okay, and the important thing, they have an explicit Gauss diagram formula for these invariants. So for the, let's say the degree is D, there will be D Gauss diagram formula. So I will not tell you that in general, just let's consider the simplest. So I would keep the loop, so let me write here. Let's consider the simplest one. So the simplest one, V2 of a diagram D is just use sum over all couples of crossing which you find in your diagram is at A, and you take the product of the sides. Okay, so the base point here, the point at infinity is between the foots of these two crossings. So this is a zero-dimensional zero-dimensional cocycle, and if you evaluate it on D, you get V2 of K. So this is a zero-dimensional cohomology class. Okay, just the first Vasily formula. So all these formulas have a remarkable property. If you come from the point at infinity, you first come to the foot of a crossing, and last you come to the foot of a crossing. Okay, so it's the first last foot property. By construction. Little side remark. This is perhaps a property of the Homfly-Petit polynomial. My student Butian Sang has played the same game for the two-variable Kaufmann polynomial, and they do no longer have this property. So this distinction, another distinction between Homfly-Petit and two-variable Kaufmann polynomial. Okay. So how we do use it? We plug this into our triple. So we have now my triple crossing. I consider this type. So this is here. I will have the point A is here, point B is here, and this here should CI. So this here was the crossing HM, my definition, and we will define VD of HM. This is just all contribution, all configuration, where HM is the first crossing in my configuration. Here's the first foot. So there are no foots or heads on this arc. So HM, first foot crossing. And the last foot should be in the arc. Last foot should be here, from B to A. Last foot. Okay. And we sum up only over those. So, for example, yeah, let me make it red in this. If we take D equal 2, we would have only two thoughts. We could have that or that. Oh, you see, here I don't have, this is the first foot, and the last foot is from B to A. Okay. Then we define the condition. V D plus 1 TE. This is just the sum over all, which are like that, A, B. This is TE. And here we take sine P, V, D, M times V. So the sign of the crossing HM will not enter. We take plus is the sum over all these. CE is A, B is now here, and minus the same thing here. Minus the sum of the same thing. Look like that. Here the triangle is in the other direction. This is CE, here's A, and B has to be here. Okay, yeah. That's the definition of a DED coaching. And the conjectures. B plus 1 AE peripheral one cocycle. For each Gauss diagram formula. Evidently for each theorem. And the theorem is true for D equal 2 and D equal 3. In general, it will be a difficult conjecture, but so for some low degrees, yes, for degree 4, there's one of the finite type invariance of degree 4 is just the coefficient in the convex polynomial of z to the power of 4. For this one, I probably can do it too. But okay, for the moment, we have it for 2 and 3. So how we will apply that? Application. So let's just take take 2. So we evaluate B3 TE on our loop which is called push to K to gamma. Of course, we know it should be 0 because the loop is contracted. But it consists of 4 parts. We have this part which we see, which can we calculate, and we have this part which we see, we can calculate. So we have this equal to push B2, B3, push 2J, okay, minus B3, B push 2J prime, okay. Okay, let us call this difference for short and right delta 3CE K. So it depends, of course, it depends of the diagram D prime and of the coordination component CE. But let us for short and right divide it like that. And then come the value of this sides plus CE to gamma minus 3 plus the C of minus 2 gamma. So the first thing is one believes that they should cancel out because so we see the same thing here, but in the other direction. So all the signs of the moves have changed. But the point is this not to K. Yeah, this is not point K. Here it was on the right, and here it's now on the left. Okay, we have the 2K has changed the position. In the solid torus, that wouldn't change anything because we could just bring it to the other side in the remaining part without any Rademacher moves. But for our peripheral one-cut cycles, it changed. But the point is, we can see this difference. So where comes the difference from? So let's consider this one. Here was A, and here was D. Okay. So all the crossings here which are not in 2K, they will cancel out. That's clear. So there are crossings 2K. If I look at this side, I say I come to 2K just before I come to the point that's infinity. So I will see here a small knot K, and here a small knot K. Because for the double, each crossing becomes 4 crossings, okay? And I will see 2K crossing, 2K, which goes like that, from one branch to the other, okay? So I see on one side I have that, and if I consider for D equal 2, so I have only to care about the crossing, you can come from here to here, okay? They will contribute. The crossing, they are exactly vaguely easy to see crossing which to them. Yes, it's the right of or not K. If I will now on the other side, K is just after the point at infinity. It looks like that. Oh. Here's A, B. Now here's a small knot, here's a small knot, and we have out okay. But they will not count because of the property. HM has to be the first crossing in our configuration. There will be this stuff between A and Z, so they will not count. So it will count only on one side. And you see from the 3 configuration which we have considered, if the point B is here, it doesn't matter because it goes from A to B, which will not cut this. But in the other case, that case of that, P. Here is A, here is B. So HM should be the first crossing, so it comes from here to here. So it will count. Okay. Again. Yeah. From here to here. This will count too. So let us now I can erase it. Let us introduce variables. So let us define xi. Sum of Superman sine p of all p in 2 gamma, which are this type. A, B. And YE, and this is P, of course. It's the sum sine P of all P. So here A, B, and this P. Okay. This thing depends only on gamma, and doesn't depend neither on which one good cycle we consider, neither which auxiliary knot we consider. It depends only on that. Hence, we get the formula. So the formula will be just that. We take times x minus e. That will be in our case how much we have called it beta 3. So we can use it to express. For example, we get immediately 1/3 delta 3 plus. This is the same thing 1/5 delta 3 and 5. Okay. The point is that we can we take now we go now the one-cut cycles of higher degrees. So there will be more variables, very complicated variables. But we can vary the degrees and vary the knot, and we get linear system of equations. And we can solve the equation to eliminate the higher variables. And we come, for example, to that. Using that, we can prove the following. This x minus x could also be equal to 1/10 delta 4t. I will not tell you what that will say for 1 plus minus 1/6 delta 4 t 3/1 plus, and should the same thing minus 1/2 delta 4 t 4/1. Okay, just in the same way. So we consider this expression. We have a diagram D and diagram D prime. We fix the zero crossing, positive zero crossing in D, positive zero crossing in D prime. Okay, we can calculate this thing, and we take this combination. So up here, this has no meaning, but it turns out if there is regular isotopy with a cobordism component, which goes from this crossing P to this crossing P prime, then this number which we have calculated here has a geometric meaning. It is just an algebraic number of times a branch goes over this crossing. So in a certain sense, and this is generalized for higher degrees. So it should, so because it is the same, it doesn't depend of all the rest. It should be the same. So we can vary here or not. Each time we get an equation. So we get, for example, this identity. This here should be equal to this. So why should it be equal to this in general? But we know if there's a regular isotopy, then it should be equal to this. So we have to make calculations and see if it leads to a contradiction. So if say if we take two crossings and these things will be not the same, then we know there is no regular isotopy which brings this crossing to from D to this crossing in D prime. Okay, so I don't know yet will it work. My student Butyan Sang has written a computer program, but I asked him perhaps too complicated thing. I like that he applied just to the most interesting thing for me. It takes a standard diagram of 817, you flip it over, and then you change the orientation. So this would be minus 817 as a long knot. And you make this thing, and you see, will you get a contradiction? He says, unfortunately, the memory of his laptop was not high enough, so he couldn't do the calculation. But it will be done, and we will see. So it's a very exciting thing. So it could perhaps give just some combinatorial identities. Of course, we can always calculate these numbers, so we get a lot of fine information about isotopes which perhaps do not exist, but we cannot exclude them. Or it could give a contradiction. And what would we do then? Just 1 minute. So we have here our D prime, here our D. So we take here, say, a zero crossing positive. We take here a zero crossing positive. So we suppose that there exists a cobordism component which connects them. There's a regularity which connects them. We get a contradiction. So we know this cannot happen. So then we take the next one, zero positive. We try this one. If this, perhaps we get again a contradiction. So this cannot happen. So we go over all of them, and then we have to go here the zero with a minus, because the cobordism could look like that. It's exactly the same equation, exactly the same thing. And perhaps we get again a contradiction. If we get a contradiction for all of them, then we are done. We know the knots are not isotopic because they do not verify that linear system of equations. And if this would really happen, then of course it would open a wide perspective. Say, if we are lucky, we could just one possibility would not be ruled out. So then we consider the next crossing here. We know already it cannot go there because this one is occupied. We make the same game. If we are lucky, just one will not be out. And it could be that we can completely determine the cobordism. So we know which crossing has to go where. And then for the interior of this regular isotope, our one could say is lots of information, which crossing goes, how often over which crossing with respect to the position of all other crossings. It could be this gives us a hint that we could construct perhaps the isotopy. So that's would be, of course, a great outcome. You were using a very deep result of Covart. Covart has proven, I think, 2006, that you can alter the Reidemeister moves. So in our case, you can make first all Reidemeister moves, which increase the number of crossings, or Reidemeister 2 moves, then only Reidemeister 3 moves, and then only Reidemeister 2 moves with decreased crossings. So the Reidemeister 2 moves are only important for the cobordism components. And for the middle, this will be a sort of braid with some strands inversed. Our one-cut cycle gives a lot of information. So who knows? It's too early to think about it. We first need to show that there are cases where it rules out some cobordism components. So sorry, I'm already over time quite a lot. Excuse me. But I was the last talk, so I think it's not so.
Wow. Thank you for this amazing talk. Yeah, there was a lot of enthusiasm that you transferred to the audience, I think. It was like seeing a conjurer. Excellent. So, yeah, I should stop recording before even talking.